In this lecture, we're going to have an introduction to multi-axial plasticity for fatigue analysis. I do teach a class in plasticity, and we get into a lot of the details in that class. So for this lecture, I want to show students how what we already know about plasticity in the uniaxial sense can be extended to the multi-axial sense, and in particular for applications in multi-axial fatigue. It's going to be kind of a brief overview, but we'll hit a lot of the highlights that I think are important to know if you are a fatigue analyst and need to do some multi-axial plasticity. All right, well, we're going to try to draw some analogies to what we've already learned about uniaxial plasticity. If you recall, we talked a lot about the Ramberg-Osgood equation in our class in fatigue, and we said that we had a stress-strain curve that we can get from a uniaxial tensile test. And what I'm drawing here is I'm trying to show the true stress-strain curve, and that's what we typically use in a lot of plasticity analysis. So I do want to keep it to that. So the way we would get this curve would be we would do a tensile test on a material. We would have some way to convert our engineering stress and strain to a true stress and strain, and then we can describe this curve in a number of different ways. One way being the Ramberg-Osgood equation. But the important thing I want to point out about the Ramberg-Osgood equation is it really has two parts to it. If we were to look at the total strain, it's composed of an elastic strain, which I'll use with the superscript E, and a plastic strain part to this curve. So the elastic part would be sigma over E, the uniaxial stress divided by the modulus of elasticity, and the plastic part would be whatever fit we're using. If we're doing Ramberg-Osgood, then it would be sigma over K, for example, divided by 1 over N, the strength coefficient and the strain hardening exponent. Well, in a similar way, we can decompose multi-axial strains into elastic and plastic strains. So here we could have the tensor of strain components, epsilon sub ij, would be equal to the elastic strain components plus the plastic strain components. And here I'm using this as tensors. Now, if you've had a class in elasticity, we go into great detail about what it means to be a tensor and so forth. If you haven't had that background yet, that's okay. The way to think of this at this point is that this can be thought of as like a matrix of strain components, where we have on the diagonal term what we call the normal strains, epsilon x, epsilon y, and epsilon z. And on the non-diagonal components for the symmetric strain tensor, we have the shearing strain terms. And instead of using the symbol gamma, I'm being a little careful here. I'm using the symbol epsilon. So we could have, for example, epsilon xy, epsilon xz, and epsilon yz in these locations. And likewise, we can decompose this into a matrix of just elastic strains and a matrix of just plastic strains. I do want to make a little note about these shearing strain terms that I have here. The epsilon xy is known as a tensor shearing strain. And you have to multiply it by 2 in order to get the engineering shearing strain. So if I wanted the engineering strain that we typically think of, when we do strain gauge measurements or so forth in mechanics of materials, the engineering shearing strain is equal to 2 times the tensor shearing strain component. Now that will have some effect when we go to do some calculations, but the concepts will be very similar to what we can talk about. And so I'll just say the shearing strain, and it'll kind of depend on the context of what I'm talking about. So whether or not it's a tensor shearing strain component or an engineering shearing strain component. Again, when we get to the point where we need to do actual calculations, the distinction is very important. From our perspective right now, it's not as important at this point. Now, just as we do for uniaxial stress-strain relations, we use Hooke's law to relate elastic stresses and strains. We can do the same thing to relate elastic strains to our stress state. And now, instead of using just uniaxial Hooke's law, we're using a full 3D Hooke's law or generalized Hooke's law. You can have anisotropic materials, but for our discussion, we're going to talk about initially isotropic materials. And so we can use our isotropic version of Hooke's law to relate these stresses and strains. Again, I'll make a note here. This is for isotropic materials. So we can have, for example, epsilon x is equal to sigma x over E, minus nu sigma y over E minus nu sigma z over E. Sigma x would be our epsilon 1,1. Epsilon x would be our epsilon 1,1 term. Sigma x would be our sigma 1,1 term. Sigma 2,2 and sigma 3,3. E is our modulus of elasticity, and nu is our Poissons ratio for the material. We have two other equations, one for epsilon y and epsilon z. And then we have our relations for the shearing strains. And for example, epsilon xy would be the shearing strain gamma xy over 2. That would be equal to our tau xy over 2g. And then we have two other equations that relate our stress state to epsilon yz and epsilon xz. Okay, so the elastic part of this decomposition of our strain tensor to elastic and plastic strains is fairly straightforward, just by using whatever we have for Hooke's law. Now the plastic part is where things get a little bit more interesting. And the way that we calculate that plastic strain kind of depends on whether we have a proportional or non-proportional type history. Now we've talked about the difference between proportional and non-proportional loading already. And this is important when we get into determining what our plastic strains are. If we have what are called proportional loads, then we can use closed form equations to find epsilon p from our stresses in a similar way. It's not exactly the same equations, but in a similar way as we do to find the elastic strains. Those are known as the Henke equations of plasticity. Let me see if I can go ahead and just write those down. It's tied to the yield criterion that we're using, and the yield criterion is tied to the type of material we're looking at. So for a von Mises type yield criterion for an isotropic material is how you end up with the Henke equations of plasticity. All right, so for those restrictions, again, for proportional loading, and just as a reminder what proportional loading means is if we were to take a look at a phase space. So for example, we have let's do it this way, tau xy on this axis, and sigma x on this axis. Proportional loading would be some sort of straight line that goes through the origin like this. Then we can use these closed form equations known as deformation plasticity, or the Henke's equations. In a time plot, these could be increasing monotonically in time, or even decreasing, but they would all be proportional to one another. And all the different stress components would need to follow this same type of pattern. Right now we're only looking at monotonic loading, but quickly we'll transition to some cyclic loading. Well, the equations that we get under these conditions, again, isotropic material, von Mises yield criterion, are equations for normal plastic strains like epsilon x, epsilon y, and epsilon z that look like this form: epsilon naught p over sigma x minus 1/2 sigma y plus sigma z. Similar for epsilon y and epsilon z plastic. We would cycle through the subscripts. And the shearing strain, again, the tensorial shearing strain components, epsilon xz plastic is equal to 3/2 epsilon naught plastic over sigma naught, tau xz, and so forth. Now here, when you define these two terms, the epsilon naught p is like an equivalent plastic strain. It's determined from our plastic stress strain curve. And if we're using the Ramberg-Osgood equation, then we put in an equivalent stress divided by k to the 1 over n power to find the equivalent plastic strain, where this sigma naught term is the von Mises stress, and I'll go ahead and write it down. We have the differences among each pair of normal stresses squared plus 6 times each of the shearing stresses squared all to the 1/2 power, and then divided by the square root of 2. Okay, so if you have a complicated stress state, you have all these different stress components, find the equivalent stress, use that to find the equivalent plastic strain, use that to determine the coefficient that goes in front of the stresses or combination of stresses, and then it works out in a way that's very similar to Hooke's law for elastic stresses and strain calculations. We don't see a Poissons ratio term in here. We do see a 1/2 that pops up. Some people call that a plastic Poissons ratio. That's really kind of a misnomer, but some people will call it that. And you might see that in some of the older literature. It kind of takes that same place, and there's some other reasons why that's kind of an important way to think of it, or a convenient way to think of it, I should say, but that's probably not the best way to describe it. All right, so this gives us a way to calculate these plastic strains under what we call proportional loading. If you have cyclic loading, then you can do the same sort of calculations and use strain ranges and so forth, and even the equivalent of the Massing's hypothesis. But the key here, and the thing that I want to point out, is what we're basing our plastic strains on is some equivalent from our equivalent stress versus equivalent plastic strain curve. And that comes down to, boils down to a uniaxial case of our uniaxial stress versus uniaxial strain, plastic strain. So this might be sigma, and then this would just be our epsilon plastic from a tensile test. Okay. So we calculate this, we find that. Basically the epsilon p over sigma naught, think of that as a slope. And you can calculate these terms that go in here and find out what goes on. This will be an important concept that we'll introduce later when we talk about structural yield surfaces. All right, well, let's talk a little bit about the yield condition and the envelope that this plots when we take a look at the von Mises yield criterion, for example. All right, and to see this yield envelope, I'm going to rewrite our von Mises equation a little bit differently. There are other yield criteria you could use, and they're just different formulas that are functions of stresses, for example. The von Mises is very convenient for a lot of the discussion that we'll have, so we'll just kind of stick with it. But what I've done is I've taken our von Mises equation and I have squared both sides. And I took the 1 over the square root of 2 and I moved it to the other side. So I actually have a 2 sigma yield squared over on the right hand side now. I have all these different terms, and I'll just do a little bit of algebra. I'm going to take and I'm going to expand these squares. So let's see, what do I have? Sigma x squared, I'm going to have a minus 2, sigma x, sigma y. I'm going to have a sigma y squared, and now I'm going to have another sigma y squared. Now I'm going to have a minus 2, sigma y, sigma z, and I'm going to have a plus sigma z squared. I'm going to have another sigma z squared from the last term. I'm going to have a minus 2 sigma x sigma z, and I'm going to have a plus sigma x squared. And then I'm going to have my 6 tau xy squared and a 6 tau xz squared and a 6 tau yz squared. Now that's equal to a 2 times sigma yield squared. All right, well, if we looked at this, we could actually factor out a 2 from these terms. So let's see, we have a, for example, here's a sigma x squared, and here's a sigma x squared. Combine those together. Then we have these 2's over here, and if we divide 6 by 2, we get 3. So I suppose we can do a little bit of algebra to simplify this down to make this look something like this. And I'll try not to do too much of this algebra in this lecture. I have other lectures where I go through a lot of the details of all of this. And let's see, I need one more. Normal stresses, I'm going to have a sigma x, sigma z. I think I have all of those in there. And then I'm going to have now 3 of these terms. And now I can get rid of the 2 on the right hand side. Now I have sigma yield squared. Now, what this represents is the yield criterion. But if we look at it the right way and think of the right way, this actually plots an ellipsoid in 6-dimensional stress space. We can look at what's called 9-dimensional stress space if we have a non-symmetric stress tensor. Or if we want to think of it in 9 dimensions, we can still do that. But there is some symmetry. If I were to take the sigma x and sigma y plane of this ellipsoid, maybe this is sigma x and this is sigma y, then in this plane it plots as an ellipsoid that's tilted, is an ellipse that's tilted to the surface. So I could have an ellipsoid that is actually in 6 dimensions, one for each unique stress component. Or if I have a non-symmetric stress tensor, I would have 9 different stress components. So in 2 dimensions, we have an ellipse. In 3 dimensions or higher, we have an ellipsoid. Higher than 3D, some people call that a hyperellipsoid. But in any event, if we were to plot one plane, then it would look something like this. And what this envelope represents, it's based on whatever number that is for the yield stress. If you have a material that's stronger, then this ellipse is bigger. If you have an ellipse material that yields at a lower stress, then this ellipse gets smaller. But it stays the same functional size, functional shape, rather. Well, what we can do with this ellipse is we can use this as a failure envelope. If I were to plot, say I only had sigma x and sigma y, if I were to plot my pair, sigma x comma sigma y, and that point lands in this plane at that spot, then I don't have any yielding occurring, and so I have only to worry about isotropic generalized Hooke's law to relate stresses and strains. I don't have any plastic strain components. So any point that plots inside this is related to stresses and strains related by isotropic generalized Hooke's law. If, however, I find a point that is on this yield surface, or would be a point that would plot outside of this initial yield surface, we're going to put some stipulations on how these points can actually be related to a yield surface. But say our initial point plotted out here somewhere, then I would have some plastic strains. So let's see, maybe we can make a note or two of this. Right, so the points on the inside, all elastic points on the surface or on the outside of that initial surface, we would have both elastic strains and plastic strains. And this idea of a yield surface is very convenient for us. There's different ways to think of it. We can think of this in principal stress directions, in which case we get something called the a cylinder and the pi plane and things like that. I'm not a huge fan of the pi plane, but that has some uses. My preference is to think of this as a hyperellipsoid. And I also like to think of this, instead of in terms of regular stress components, I often like to think of this in terms of what are called deviatoric stress components. Now, without getting into the details about deviatoric stresses, basically it is the stress tensor where we've subtracted away the average hydrostatic stress, or the hydrostatic stress, which is the average of the normal stresses. It leaves us with just the part of the stress tensor that is thought to contribute to yielding for most polycrystalline metals. Well, the reason why the hydrostatic stress, the deviatoric stress, is very nice to use is that we have a perfect circle, we have a hypersphere and 9-dimensional deviatoric stress space as opposed to a hyperellipsoid, and the geometry just becomes a little bit easier. What we're going to go through today, I'm going to probably represent this as a circle because it's easier to draw, but the same concepts apply. The numbers are a little different, the calculations are a little different, but what we want to emphasize is the concepts of multi-axial cyclic plasticity for fatigue analysis. And so I'm going to take a shortcut and just draw a circle to represent my yield surface instead of these ellipses all the time. You can always take an ellipse and, with the appropriate coordinate transformations, turn it into a sphere or a circle. All right, so with that, instead of drawing this hyperellipsoid, I'm drawing a yield surface that's a circular in shape that could represent a hyperellipsoid. But again, anything that's inside of it is elastic. Anything on it or what could be outside of it has elastic and plastic strains. Okay, so how does this relate to what we know about uniaxial behavior? In particular, cyclic behavior. So if we were to look at our stress strain curve, we know that when we first load it up, it might do something like this. And then when we unload it, we get a nice hysteresis branch. And we reload it, we get a nice, smooth, nice looking hysteresis curve. And it plots in that shape. By the Bauschinger effect and Massing's hypothesis, this region would be approximately a size of 2 sigma yield. And this would be sigma yield. And it doesn't really yield in compression until we go this distance, and it yields in tension when we have a distance like this. So we talked about how the initial part of the stress strain curve, if we were to shift the origin from here down to here and expand the stress and strain axes by a factor of 2, we would get a nice model of what that branch looks like. When we talked about the Ramberg-Osgood equation, we have a continuous yield equation. This is a little different than what we have right now when we think about these yield surfaces. These yield surfaces, we have a well-defined elastic zone and a well-defined area where we have elastic and plastic behavior. Now we could think of this yield surface shrinking down to be tiny, 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 and we would have a little bit of plastic strain everywhere. But from an implementation point of view, it's nice to have a finite yield zone, elastic zone size. So how does this relate to our multi-axial plasticity that we need to use to figure out what's going on with our, say for example, our critical plane approach for fatigue analysis? Okay, well, our initial loading in uniaxial would be along our stress strain curve up to here. Right? Where are we at with our yield surface? So with our yield surface, remember every axis represents a different stress component. I am just going to assume that as if I go up this way, that represents changing this stress component. So as I go up this way, I don't have any yielding until I hit this yield surface. I'm starting at the middle of stress space. We have a material that's never been tested before. Okay, so that represents this portion of the behavior of this stress strain curve. So the radius of this is related to sigma yield. Now, if I'm in deviatoric stress, there's a coefficient that goes in front of that and so forth. Again, if you were to take the class in plasticity from me, we get into all these kind of details, but conceptually, that's the correspondence in that one particular direction. Beyond yielding, we have the curvy part, and beyond yielding, maybe I can change to a different color, we continue on and we get up to, say for example, here. Then that would correspond to this portion. So that would be these points along this way. Now there's kind of a rule that we're going to introduce in our yield surface plasticity. And that rule is we can never really be outside of our yield surface. The most we can do is be on our yield surface. So what that means is all these different points, there's two ways to describe the behavior, but the way I'm going to introduce first is the yield surface gets dragged along to these points right here. So I won't draw the entire yield surface, but it gets dragged along to here, it's dragged along here, and it stays the exact same size, just moves up this way. So it's gone up to here. The yield surface has moved. Now, what does that do to our yield equation? Well, if we have a circle, x squared plus y squared is equal to r squared, and we have a circle that moves off the origin, then we have like an x minus x sub c squared, and a y minus y sub c squared is equal to r squared. What we're doing is we're changing the places where the center of the circle is at, or our hypersphere or hyperellipsoid, but the functional form otherwise stays the same. So we still have the stress components, but now we have the stress component minus the shift value squared, and the other stress component minus its shift value squared, and so forth. One way to think of this is if you were to have a washer or a ring and put your pencil in the middle of the ring, the yield surface doesn't move until your pencil hits the edge of the ring, and then it moves with it. So this drags it on up. Now by the same reasoning, if we were to unload this material, go back to red, if we were to unload this material, we would follow this path, and we wouldn't have any yielding until we went a distance of twice the yield stress of the material. Well, how does that work here? Well, now we're right up at here, and we elastically unload, and we elastically unload all the way until we hit this side of this black surface. Now the path that we have traveled has a total distance of 2 sigma yield. Okay, so that's how we can get a similar behavior in the multi-axial sense from the uniaxial sense. The multi-axial behavior has to reduce down to what we observe in the uniaxial case. Once we hit the other side of the yield surface, then again, think of that washer or ring with your pin having been up here. Doesn't move, it doesn't move. Your pin hits this side of the ring, and then as you move it further and further this way, then that ring gets dragged, and now your new yield surface location maybe is down here. Okay, so it goes all the way down to here. This point that was at this spot is now down here, and that's where we are down at the bottom of this, and then we just repeat this loading over and over again, and we recreate what we see and observe in uniaxial behavior. Now the power of this yield surface is that we're no longer restricted to just uniaxial behavior. If we have multi-axial stresses, we have different combinations. We can take this surface and we can drag it off at any angle that we want. We can go around here, we can unload it, we can go over there. We can do all kinds of interesting paths to figure out and calculate what our plastic strains are. Now the way the plastic strains are calculated in complicated non-proportional paths is different than what we would do just by using the Henke equations. And for that we have to use something called the normality flow rule, and we'll explain that here in just a moment. Okay, so the normality flow rule says that if you are at a point that's on the yield surface, that point on the yield surface has a certain unit normal associated with it, and we call that Nij. And the plastic strain increments, the d epsilon ij plastic, are proportional to whatever this is. So as you are on different points along this yield surface, you get different values for the components of the normal. Again, I'm not trying to teach an entire class in plasticity in 50 minutes or so, but this will just give you a little bit of flavor if you see some of these terms in some of your readings. The plastic strain increments can be added together. They're infinitesimals, but we can really think of them as small delta epsilon ij plastics. You can add those together to get the total plastic strain at the end of a path. Now there's another form of yield surface plasticity other than the one that I've just described here. And the one that I've described here is known as kinematic hardening. Kinematic hardening means that the yield surface moves kinematically, has a kinematic movement to it. Okay. Now, if you were to use a finite element code like Abacus, Abacus has a kinematic hardening plasticity option that you can use. The implementation of the Abacus kinematic hardening is what they call bilinear. So you actually only get one slope for your hardening. Instead of a continuous smooth curve, it would be kind of more of a thing that looks like this. But they have other options in Abacus as well. This is known as linear kinematic hardening, and it has a bilinear response, the elastic and then one plastic tangent modulus. For cyclic loading, which would be what you would want for fatigue, this is a better option than the next one I'm going to tell you, which is called isotropic hardening. All right, so there's my yield surface again. Now we're going to talk about isotropic hardening. I think I can spell that better. And the isotropic and isotropic hardening does not refer to the material behavior, but it refers to the behavior of the yield surface. So isotropic hardening means that when we are inside of our elastic range, it's just the same as kinematic, but once we hit the corner or the edge of this ring, the whole ring expands as we move over in space this way. So instead of having the circle dragged, we have a new circle that's a new size. And it keeps getting bigger, and it gets bigger all the same, just in the same proportions everywhere. And associated with this is a stress versus plastic strain curve. And by the same ways that we can figure out the plastic strains at every point along this path up this way, we can calculate them as well, using again the normality flow rule and our yield criterion if it's von Mises or whatever. We can find a nice response on the initial loading path of our stress strain response. In an abacus, if you use that, it's actually a very nice smooth response. It has a nice curvy feature to it. The issue with isotropic hardening, save this page, the issue with isotropic hardening is that since the yield surface gets bigger, it's not going to contract. It's not going to get smaller. Let me see if I can get rid of the intermediate yield surfaces. So once our yield surface gets bigger, it just stays bigger. Now this turns out this is not a very good model at all for fatigue loading when you have the Bauschinger effect and to worry about, because if you traveled from the center of your stress base up to this edge, now you're here and you want to get to the other side, and you travel all the way over here. Now your yield zone has expanded, so it won't yield again until it's hit the other side of this yield surface. So we have a big elastic range, and then we do that. And then when we reload it, we have an even bigger elastic range, and then we do that. So we can see that, you know, if we are not careful, this can give us some very bad results for variable amplitude, cyclic loading in particular. I'm just going to put a little note here, not usually, or not generally maybe, suitable for fatigue loading. All right, now there's another option that's very popular these days. It's kind of the, it's the default option, basically, called non-linear kinematic hardening. And let's see if I can bring up a new page for that. You'll see some various names for this. Non-linear kinematic hardening, Chabouche plasticity model, Armstrong Frederick, but this allows you to have a lot of different effects that we have talked about in our class. Allows you to have transitory plasticity. Cyclic hardening and cyclic softening. You can have things change with numbers of cycles. The advantage is you have a higher degree of being able to model what you want, but every time you ask for something more, it needs more information input into it. So if you have tons of test data, you can calibrate a very nice nonlinear kinematic hardening model. The discussion of the details of nonlinear kinematic hardening are well beyond what this short lecture will be, but I just wanted to make you aware that there are more sophisticated models of plasticity than kinematic and isotropic hardening, although those are often some of the more popular choices. All right, so what's the bottom line of what I want you to get out of this lecture for fatigue analysis class is that we have ways to calculate stresses and strains for multi-axial stress states. Let's say it this way, multi-axial stress-strain relations. And these can work for cyclic loading with the right options. Once you have the cyclic stress and strain, then we can go into our critical plane method. We can do rainflow cycle counting on our various critical planes. We can find closed hysteresis loops on those planes and accumulate damage. Do all the things that we've talked about in our discussion of the critical plane approach. The last thing I want to leave you with, I guess, is that isotropic hardening is generally not suitable for cyclic loading. Now, if you really know what you're doing and you're really careful, there are some cases where you can use isotropic hardening and then use that information to, with say Massing's hypothesis, to develop cyclic histories, but you have to be really careful with it. Kinematic hardening models are better. Nonlinear kinematic hardening is the most sophisticated but requires additional input properties. All right. So again, I have a whole series of lectures. If you're watching this on YouTube, I have a whole series of lectures on plasticity, so I'll refer you to those. For those of you that are in my fatigue analysis class this semester, I think this is adequate enough for our discussions on this topic for our class. And if you would like, I'm offering the plasticity class next semester, and you can sign up for that, and we'll get into all the details. We won't have any necessarily programming assignments due in that class. I think most of what we need to do can be done with the use of Excel spreadsheets. So it might be a little bit easier than what you've had to do with your rainflow cycle counting algorithm this semester. All right, with that, I think that'll do it.